welcome to part 2 of lesson 18.3. We had just gotten done talking about doing ray tracing with concave lenses and convex lenses. Convex lenses, in general, you can get right side up images, you can get upside down images, you can get smaller images, you can get larger images. It really depends. In a concave lens, it doesn't depend. You're always going to get virtual, it's always going to get smaller, and it's always going to be real. So, here we go. We're going to now talk about how do you find it using the lens and mirror equation and the magnification equation. So we've done this in the last chapter. Now, be careful. Remember that the focal length is positive if you've got a convex lens. It's going to be negative if you've got a concave. Remember here, the distance to my image, that's going to be positive if it's real and negative if it's virtual. The distance to my object is always going to be positive. Here's our first example problem. It says an object is placed 32 centimeters from a convex lens that has a focal length of 8 centimeters. Where's the image? Is the object this tall? How tall is the image? And what is the orientation of this image? So the first thing I could do, I could make like a quick sketch of what's going on here. Here'd be my focal length, and that's going to be 8 centimeters. My center of curvature is going to be out here at 16. This thing is placed 32 away, so it's actually 4 times as far. 1, 2, 3. So my object is going to actually be placed out here at 32 centimeters. So I could get a quick guesstimate as to what I think this is going to look like. Ray 1 comes in here, it goes through the focus. Ray 2 goes through the here. So I'm going to say, I know that I'm going to get a real, it's going to be inverted, and I know it's going to be smaller. So all of these things should match up with my math. But let's write down what I've got. I know that the focal length is 8.0 centimeters. The distance to my object is 32.0 centimeters. I'm looking for the distance to my image. Well, first of all, I can do this. So 1 over 8, 1 over 32 plus 1 over distance to my image. So I take 1/8, which is actually 4 30-seconds to make this common denominators. 4 30-seconds minus 1 30-second is 3. 1 over di. So I flip both of these. So di equals 32 over 3. Or 10 2/3, so 10.7 centimeters. So the distance is 10. And if you look at this, you'll look at this distance right here. It's a little bit farther because remember my focal length was 8, so this looks about right. Even my sloppiness, 10.7 centimeters. Now notice it's positive. This is when it's positive, that means it's real, which is what I said at the beginning. I predicted it was going to be real, so I should get a positive number. The picture should match up with your math. That's part A. Part B, if the object is 3 centimeters tall, how tall is the image? So what I'm going to do is take my magnification equation. Hi over ho negative di over do. The height of my image is what I'm looking for. Height of my object is 3. The distance to my image was that 32 over 3. It's fine. I'm going to put it back in that form because you're going to see how kind of clever this works out. And then the distance to my object was 32. So check this out. I'm going to cross multiply. What is 32 over 3 times 3? Well, this cancels off, and it's 32. So I get, when I cross multiply, I get 32 then when I cross multiply this way, I get, well, actually, I should make sure that that's negative. And then I get 32 HI. So solving this is fairly easy. The height of my image is negative 32 divided by 32 is negative 1. Now remember how I told you before that it was inverted? That's true. This negative shows that it's inverted. And that's good. Everything's matching up. And then part C, what is the orientation? That's inverted. That's what they're looking for with orientation. Inverted. So that's how we use the lens and mirror equation. I could have done a scale drawing. I didn't have to go through all this math. I could have done a nice scale drawing with my picture and gotten the exact same numbers. But the math is a lot easier to work with than busting out your ruler to get a nice scale drawing. Now how does this image change? How does this problem change if instead of it being convex, what if we put it in front of a concave lens? Like change all this around, put it in front of a concave. Well, first of all, the focal length isn't going to be positive 8. In this case, when you have a concave, the focal length is going to be negative. So here, let me just draw a quick and dirty example for what I think this looks like. So again, we've got this out here at 8. My object is going to be way over here. Uh-oh. Ray 1 is going to come in, and it's going to go away from this focus. And then the ray 2 is going to go through the middle. So my object is going to be here, my image. So I know it's going to be virtual, smaller, and upright. Remember that in all cases that's what it is. So how do I find this one? Again, the distance to my object is going to be 32. My focal length is going to be negative 8. I'm looking for the distance to the image. So 1 over f. So 1 over negative 8 equals 1 over 32 plus 1 over the distance to my image is unknown. So this becomes kind of simplifying. I'll make negative 4 over 32. So negative 4 over 32 minus 1. I get negative 5 over 32 equals 1 over di. So I flip both of these, and di equals 32 over 5, which also equals 6 2/5. So that's 6.4. So it's negative. Now that makes sense. Take a look up here. See how this distance is less than 8? I think it's negative 6.4. And it kind of shows, even in my really rough drawing, that it's really close. It's less than the focal length, negative 6.4. So this means it's virtual. When that is negative, it means virtual, which checks out. How tall is my image going to be if it's 3 centimeters? So hi over ho is negative di over do. Height of my image, unknown. Height of my object is 3. Negative, distance to my image is negative 32 over 5. Oh boy. And then the distance to my object is 32. So again, I cross multiply. So I take this one times this one. So 32 times 3 is 96. So I get 96 over 5. And that's positive. And when I multiply these two, I get 32 hi. So I divide both sides by 32. so I get HI equals 96 over, I can just put the 32 down here, and this can come out of there, and that'll be 3. So I get 3/5. So HI is equal to 0.6 centimeters. And notice how it's positive, which means it's upright. Notice how the number's smaller than 3, which means it's smaller. The image is smaller, that means the image is upright. All these numbers, when you compare them to the originals, tell you the exact same thing as the picture. Alright, so in summary, why do we get upside down, right side up images? Depends upon where they are and the refraction of the lenses. Why do we get an enlarged or shrunk image? Same reason. If you're in front of a concave lens, it's always going to be smaller. Depending upon where you are in front of a convex lens, you could get a larger, could get a smaller, and you can get a same size image. And you can also get no image. Is there a relationship between? Yep. What types of lenses are there? As far as I know, there are 6 types of lenses, convex and concave, and there are 3 subsets of each of those. 2 subsets, double, plano, and concavo-convex, convexo-concave. Thank you very much.